Jumping air gaps. I'm Monta from FoxGuard Solutions. We do patching and industrial control system equipment, your relays, that kind of stuff. And we're here to talk about jumping air gaps and maybe have a little fun along the way. We'll start a little silly, maybe get a little more serious toward the end. All right, so quickly, what's an air gap? Well, it doesn't actually mean no air. It means that we don't have a network of any kind set up here. Right? So we've got this little piece. Oh, this has got oh, good. So over in this corner, there's no network already set up. There's no network communication in and out. This is air gap. The rest of the universe has all different kinds of communication. But in some places, we specifically don't allow that communication. We don't want it. It's too dangerous, okay? But there are not very many places that do that. And I'm also going to ask for a small concession. We're not going to talk too much, actually, about software vulnerabilities, believe it or not. But who here believes that software vulnerabilities exist? Oh, good. It's good to be in front of believers. And that these things happen. So I'm going to make the assumption that I have the ability to move some code around, whether that's with a vulnerability or a USB drive or something. I mean, we get one-time sort of code execution in lots of places. And the question becomes, I think, as we move toward the end, and is Rob Lee, is he around? No. But, Rob will tell you that planning events take time, right? It's often not the one communication. It takes time to understand a network, to understand a process, and how to take most advantage of it. I guess the final word of air gaps at the beginning. What's the biggest air gap that we have for a control system? What do you think? Anybody? Come on. Yeah. Yeah. Voyager 1. What about manned? Manned people, the furthest people away. What? Do we have people that, oh, no, that's Iron Sky. I'm not, who believes in Iron Sky, the movie with the people? You don't count. Anybody else? All right. But you're close. What's close? I heard somebody. Come on. International Space Station, is that what you said? Okay, right. Who knows, have they ever gotten a virus? Yes, they have, and they're pretty air gapped. So we'll talk about, we could probably get code at particular places at least one time. All right, so I've got a couple of toys here in the back to reach. And we will talk about this in a minute. And I cannot believe what kind of torture tests the TSA puts this stuff through. I'm completely redesigning this when I get back. What? That's crazy. All right. Here we go. So here's the first little bit of fun. This is this device that we created. It's based upon an Arduino-compatible device. It's got a very simple photo sensor in it. With it, we can pull data through the CapLock Light off of a keyboard. So what we do is we modulate things like passwords on the CapLock Light and then read it off using this device. So when you start talking about different paths and different ways to access things. Now, this is more common in corporate environment. Who knows or runs DLP? DLP, anybody? What's DLP? Data loss prevention. Is it looking at your shift lock or your CapLock key light? Probably not. It'll detect USBs when you plug them in and maybe stuff going across the network. So a little bit of fun. And in some ways, one of the trouble that we ran into modulating this CapLock Light was it turns out it's already modulated. Somebody's doing a pulse width modulation to control the brightness on these things already. So we have to modulate on top of that pulse width modulation to pull data out of it. So that's a little fun, light around. And this is an absolutely brand new attack, right? No, this stuff is old as as physics, really. I'm wearing the wrong watch. I bought this watch recently. It's from about 1995. You see the little hole up at the top? Want to take a guess what that is? No, it's going the other way. So that is a light sensor. This is a data bank watch. You programmed it, now get this, by holding, did you have one? All right. Do you still have it? Maybe. So you hold this up to the monitor and it blinks data into your watch so you can keep up with the 6 appointments or whatever that it'll store, right? So, and as I understand, it doesn't work very well on CRTs. You have to have the old monitors to actually modulate light. And so we've been sending data this way for a long time. And you're going to see this theme as we talk about old attacks, current attacks, maybe new attacks going along. But again, to think about the different concepts and the different ways to do this. Anybody use one of these? Come on, raise some hands. I don't want to feel out of place here. All right, yeah, at least half the audience. So a modem. This is from the 90s, maybe the 80s era. We've got a couple of lights here somewhere. They're usually like TX and RX, and so these modems have LEDs that blink as the signals are sent, and blink as the signals are received, generally as a diagnostic aid. But guess what? LEDs are fast, and particularly early on, they were tied directly to the data line. So what does that mean? That means the data that's going across the line is blinking on those LEDs. Right? And some of you people know, I think it's an old NSA story that once people realized that, there was a case where they set up in a building across the way and looked through at the modem in the other building and pulled data off by reading those LED lights. Right? So this stuff is as old as technology, really. Ultrasonic. I built one of these. Hang on. I built one of these. It's an Arduino. I've got a little, as soon as I can find the right button, a piezo sensor on here. It's just a microphone. It's a speaker. It's kind of biased toward higher frequencies. And in particular, it's really easy to modulate at like 40, 44 kilohertz, somewhere up in that range. And what's interesting about those frequencies for people? We can't hear them, right? And particularly the older you get, the less of them you can hear. My kids can hear about 6K higher than I can. So this is a data communication that you can't hear. We wrote an app for this phone so that we could transmit data from a device to this app in the phone. So we have a special piece of equipment. A cell phone is pretty complicated hardware. You're going to maybe give me that we can get software on things. But wrote an app to transmit. You can probably get across the room. We'd actually originally planned to make the app available, so if you guys wanted to download it and send text back and forth on the plane, because you could do that, it's not RF, just to have fun, but we decided we didn't have time. So we can modulate ultrasonic, and we've seen who's read the attacks, right? Anything with a speaker, pretty much. If your computer has a speaker, lots of things that move. Tim mentioned, the drill attack. If there's something I can modulate, some kind of drill motor, some kind of speaker motor, some kind of, variable frequency drive, something that moves, you can probably generate sound, and that becomes a path to transmit data. It's not particularly new. Whoa. Well, you're my buddy this time. You have one of those? I heard about them. I didn't have one till recently. I have this one. All right, other than you, who knows what this is? A clicker. And I like that you said clicker because I'd always heard like these things called clickers. I didn't realize that, hang on. Right, these things, they really click. So, I don't know, these are probably 60s time frame, maybe 70s. 60s? Okay, I'll take your word for it. And believe me, I'm totally amazed. How many transistors do you think they built this out of? Come on, give me a guess. Oh, somebody said it. 0. There are no transistors. How many batteries? 0, nothing. It's all mechanical. If you look down in the end of this, y'all can come up later if you want. If you look down in the end, they're aluminum rods that are tuned to different frequencies based upon their length. And when you hit this, there's a little hammer in there that bangs them. So it's actually ultrasonic. I also built a remote control for my, anybody here have an Amazon Echo? I built a remote control so I could do this and control my Echo. There's a video of it somewhere. All right, so what are other paths we can use to play, with jumping air gaps? Where can we send digital data where there aren't specifically networks included, and how do we do that? Another way is RF. So, and in particular, and for this one, I just combined both of them. I mean, it's ugly here, but you see this little LED? I can modulate radio frequency that I can pick up with some additional hardware. In this case, we're talking about a software-defined radio, SDR. If you hear me say SDR, software-defined radio. And I can read that, way across the room. Maybe farther. I'm not really pushing this for distance. It's for me to learn and to maybe show off for some of you guys. By the way, this LED helps a lot because the dumber the device is, the harder it's easy to modulate RF, it's easy to generate RF, all these equipment do it, but sometimes you want higher frequencies, and this processor only runs at like 16 megahertz, and so I can only do lower frequencies. The lower frequencies want larger antennas to propagate well. So now I'm looking for long traces on PC boards, or I'm looking for wires like to this LED. That makes my transmission range much farther and much clearer. And if you look at Shannon, Claude Shannon, this information theory, it's a trade-off between how much noise you have and how fast you can transmit data. So to some extent, theoretically, you can transmit, at an infinite distance at a 0 rate sort of thing, but you can trade off sometimes noise for distance. And something like this wire, this LED helps. It gives me some wire. Another interesting piece is that the computers that we use now they have lots of capability, and they're very configurable, meaning that I can usually change the function of any of the wires coming in and out of a processor, particularly for microcontrollers. I can change their function. They could be output, they could be input, they can be analog to digital, sometimes they're digital to analog. They have lots of different functions. Now, an LED wire, don't laugh, an LED wire is a good opportunity for me because it's probably already an output, and because we like to change the brightness and things we've already talked about, it's probably already set up to do pulse width modulation. So I'm playing with that pulse width modulation to generate radio frequency that I can pick up from dedicated hardware elsewhere. I'm still going to get this right eventually. So, but it doesn't necessarily have to be an LED. Most of our devices have switches on them or buttons on them, and those buttons are read into the microcontroller. You push the button, you turn on the switch. The software reads a thing. We've talked a little bit about that in some of the earlier talks. The software reads it and does a thing. Well, since I can generally remap the function of those lines, instead of being an input, I can make it an output. And why do I want to do that? So that now I have something that has a wire. A wire helps me at lower frequencies and larger distances. So I'm looking for lights, I'm looking for LEDs, I'm looking for switches, I'm looking for anything that has a wire because that helps me out. This is the graph off of a software-defined radio, SDRs. I'm sure some of you guys, who's playing with SDRs, software-defined radios? Yeah, we got a handful out here. At the lowest level, $20. And the software is free. And you can start looking at radio spectrum from maybe 20 megahertz up to a gig and beyond, depending on what kind of SDR you have. I think they were originally, a lot of the cheap ones were originally designed to be television tuners for people who want to watch television on their computers. And somebody decided, well, if it can receive these signals and it can do these fancy things, we can use it to read and decode all kinds of radio signals. Right? You can decode, I decode tire pressure sensors because all of you people who has a car that monitors the tire pressure and lets you know when it's low, right? All of us have a serial number, right? So you can read those as they go by. You can do, you can pick up these FM mics. You can do lots of different kinds of decoding and demodulating. So that's a lot of fun. But these small devices are built with some specific hardware. They generally include an antenna of some sort, and then a low noise amplifier to boost the signal up. Then they'll also have a voltage-controlled oscillator and a mixer to help them pick the right frequency, and a digital analog converter. So this is some specialized hardware. It's not expensive, but it's specialized, and generally you don't find it laying around a lot. I mean, you might find it in a cell phone, but you don't find it necessarily in a lot of places. But we've been doing this for a while too, right? Here are some computers from the 60s and 70s. It's a PDP-8. And that's the Altair. People started with these PDP-8s, again, back in the 60s, and they realized by changing the loops in the code that ran on these, they could generate music that you could pick up with specialized hardware. What was the specialized hardware? A transistor, an AM radio. Right? So you change the loop, you get different frequencies, you play simple songs. We've been doing this forever. It's not particularly new. Maybe sending data over it, ad hoc is a little new. But again, most of these technologies have been around once you go looking for them. I bought this on eBay. This cost me $7. You know why it cost me $7? Because the ones that cost $3.98 were sold out. It looks like a USB charge cable. It is a USB charge cable. But if you look, you can pull the little case off and put your SIM card in there. So if it's a SIM card here in the end, and you can tell it to transmit voice and GPS coordinates. This is $7, right? The people who buy expensive ones can probably do the data across the cable. This one won't do the data across the cable. It'll just give me voice and GPS location. So again, yeah, maybe this is a little more future, but past, present, future. We've been doing these kinds of things for a while. Put this back up before I lose it. I like this thing. They might be sold out. Go to your favorite Chinese suppliers. No promises where else it tees off the data to. That's up to you to figure out. The thing. I see same people laughing. It's one of my favorites of all time. So in about 1945, a bunch of school children in Russia presents this hand-carved Great Seal of the U.S. to the U.S. ambassador there, and he takes it and he hangs it in his office. And it stays there for 7 years and 3 ambassadors. And then they discover it's got something inside of it. Yeah, go figure. But not only that, it's really cool. I mean, I think it was extremely sophisticated technology for the day. There's still basically no electronics. There's no power. There's none of this. It's powered remotely by microwave. So they're beaming microwaves, and the microwave can pick up changes in this resonant cavity and modulate the sound back across a radio signal that they can pick up. That's great, right? It's not transmitting when you're not sending it power. It doesn't need power locally. Fantastic hardware. And this is from the 40s. So we've been doing this for a while. But that thing's great. You get it from the school kids. I mean, come on. That's awesome. Oh, they have, I don't know if it's a replica or the real one at the NSA Museum up in D.C. You should go check it out if you get the chance. So we have air gaps, but they're often impractical because sometimes we do need to get at least some data. Right? We want something. If we have some kind of plant, we want to know the product of that plant, or we want to know what the vibration is, or we want to know how it's performing. So air gaps are somewhat impractical. So we come up with this better solution. And the better solutions are, in two pieces. There are two ways that this can work, but what if we had a network that would only go in one direction? So if you have secrets, if you have something that you want to keep secret, like maybe you're an intelligence organization of some kind, it might be nice to be able to collect data, but make sure that no data can go back out. This is a single direction function. This is a diode, right? That comes from the electrical term of diode that only allows electricity to flow in one direction. Now, that's okay for secrets, but for assets, we generally want this to turn around and go the other direction. What we want is we want to be able to find the right button for the laser. What we want is to be able to send data out about performance, you know, what's the generation, what's the vibration, what's going on in this, without anybody else being able to send control data back in to control this. So, the great solution is this data diode. And this data diode is based upon the concept, and sometimes might actually be, a device that will allow electricity to go through a path in one direction, but not through the other. So this diode represents power that can go in this direction. And, well, wait a minute. Who believes that holes are things? Sorry, it's an electrical engineering joke. But so that believe that power can go in this direction, but not this direction. And that device physically enforces that. That's what it does. You know, that's the physics of this device. So let's talk a little bit about how this works in operation. That's a little small. We'll skip ahead one to this one. So this is the patent from, what was it, 97. And look, we were doing stuff similar to this before this patent. I know I was. But anyway, so the way this device works is the key things are these two blocks. And what I want you to imagine is between these two blocks is imagine this side is a flashlight and this side is a solar cell. Okay? We'll do this again. This side's a flashlight and this side's a solar cell. So now, when we want to send data, what we do is we can turn on this flashlight and we can read it with this solar cell. And that's amazing, but we cannot make this solar cell generate light, and we can't make the flashlight read it. Oh, see where I'm going now? Now we have physics that enforce this data diode direction. It physically can only go in this single direction, from the light to the sensor. There is no way to go in the other direction. Physics doesn't allow it. It's not a thing. One early problem with this data diode is who plays with TCP, right? TCP packets. What's the first thing they teach you about a TCP connection? The three-way handshake, which means before you can talk in TCP, you have to be able to send a packet one way and to reply the other way, and then you can run this connection. Even though you think you're sending data in one direction, even though you think this, we'll say FTP, hopefully that's considered an old protocol, but even though you think you're sending data in one direction, you really have to be able to send packets in both directions for that to work. So this fantastic data diode that will absolutely protect us can't do TCP, but we need to do TCP. So what we came up with was the unidirectional gateway. And so my fault, sometimes I will use the term data diode and unidirectional gateway interchangeably. Cut me a little slack, will you? But a unidirectional gateway is something a little different, and it fixes this TCP problem. So with it, what we have is we have a computer on one end. Now imagine we are trying to send a file by FTP, File Transfer Protocol, hopefully an old method, but relatively simple, from here to here. Well, we can't do it because we can't get packets back across this data diode, the actual diode part, the flashlight and the solar cell. So what we do is we have a computer on this side that will talk TCP to whoever wants to talk to it on the, let's say, the inside of your plant, and will receive the file. Then using its own special protocol that's not TCP, that's something special, it will send it to the other side of this data diode. And then the computer over there can send this by TCP to whoever else needs it. That way, nobody has to talk any special protocols except these two little pieces right there. So that's our unidirectional gateway, and that is, that's the ultimate in data protection. Now, you see in this early patent that perhaps, well, what happens if the file doesn't get there? That's what TCP grants us, is if it doesn't get there, it lets you know. If the file doesn't get there, you're out of luck. You've got no way to know. Because if you're trying to send a file from here to here and it doesn't get there, you've got to be able to tell them that you didn't, and now you can send data in the other direction, and you broke the whole reason that it's there. Now, occasionally, people want to fix that too. We'll ignore them for a minute, but here where they have a horn. And that's a pretty good solution, because now maybe this horn goes off when the file screwed up, and that means a person has to walk over to this computer and push this button and say, send it again. Nobody can do this, automatically from across the ocean or from anywhere else. So not bad. And, you can't send a lot of data back across this horn through a human. So that works pretty well. These data diodes are called unhackable. Why are they called unhackable? And, it's a good term. Think about a firewall for a minute in contrast. So we have a bunch of computers on this side of the firewall and some computers on this side of the firewall, and this firewall is enforcing some restrictions. Now, is this firewall unhackable? Well, in this context, what we mean is that even if, assuming I am allowed to put any kind of code that I want to on this firewall, can I make packets go back and forth? If I can change its config, if I can change the software, can I get packets to go in both directions? Yes, of course I can. Of course I can. But in this unidirectional gateway, in this data diode, if I can put malware on both of these computers, and I get to run whatever code I want, I can still only transmit with the flashlight and receive with the solar cell. So it's unhackable. There is no way to send information in the other direction, even if you control both sides of the device. That's what we mean by unhackable. And that's the challenge, right? Somebody threw down the gauntlet, so let's have some fun. I think I probably need a volunteer, because I want to talk while somebody else runs the. Oh, you're a sucker for punishment. Come on up. You moved fast, man. He was on the show. All right. So, hang out here just for a second. Yeah, that's good. Yeah, look pretty for the camera. Okay. By the way, another patent for data diodes includes using an optoisolator. Optoisolator is this flashlight and solar cell both contained in a small chip, like this. And this is actually the chip that we'll be talking about and I'll be using. So inside this chip, you see on this side there's actually an LED. That's a little light. And it will send light to this transistor that will change state when it gets light. And the wires on this side never touch the wires on this side. It's literally light inside this black colored box, and it can only go in one direction. Some of you might say, okay, you can use LEDs as photodetectors. Nobody cares because I have 5 volts, and I cannot get this transistor to send photons in the other direction. I tried. Look, I have a limited amount of resources with stuff like this. I spent a lot of time looking at these optoisolators. Guess what? They optoisolate. Who knew? What? It's spelled out. So, well, since you laughed, by the way, you know, I say the difference between the auditor and the hacker. When you're an auditor and somebody gives you documentation, you have to believe it. You have stuff to do. You have to go home, right? When you're a hacker, you don't believe anything anybody tells you, and you test it all out because you don't have a life and you have lots of time to spend, right? So those are the trade-offs, right? If you're going to do some kind of audit, you have to believe the documentation. And if you're going to try to hack it, it's not what was the device designed to do, but what is it capable of doing. That's your hacker's secret for the day. All right, but anyway, this device still only sends data in one direction in any kind of reasonable circumstances. So now we come to this. And here's the implementation that we have. You see? Yeah, if you look, pieces there, pieces here. Nothing up my sleeves, all right? Okay. Oh, you like this? Yeah, so 1975, this is the first LCD chronograph watch ever made. Sweet. Thank you. If you guys want to be bored for about 10 minutes, ask me about this later on. So the implementation looks like this. This is our data diode. It's up here, but this is your big picture. This is our data diode. This is the computer on one side. This is the computer on the other side. And this little bitty square right there, that's the optoisolator. This, even though it's sort of hard to tell from these wires, this one's only connected to the ones on this side, and this one's only connected to this side. So there's no electrical communication. The only way you send packets through this device is optically, you generate light and you send it through. One more note is that although this diagram is drawn so that it's supposed to send data in this direction, mine, as you can see from this diode up here, is supposed to send data in this direction. The LED is on this side and the sensor is on the other side. So this is our implementation for today. The other pieces represent our balance of plant. We have some power down here, and this is our cooling fan or our liquid pump or whatever. On this side, this is our output gauge because we want to know what. Well, so the vertical white line is actually where data. This may or may not be housed in a single box. I would say the red line. Well, the combination of, right? Because this red thing, this is the unit. The red is the data diode. The white is this dividing line where we can only send data in one direction across it. Yes, no, thanks. I appreciate that question. So everything encompassed in this red line is the data diode. And if you buy one of these commercially, right, this is a mock-up of what that might be. And this line says we can send data this direction across this line, but there's no way to send data this direction thanks to physics. And then we can reset the device. Okay, so well inspected, ready to go. Oh, let's see. We got to put the little light up too. We should take a vote. What's most common is, does green mean good or does red mean good? Because that always confuses me in these plans. All right, so for this one, green means good. Let's see if we get a green light. No, we don't get any light. There we go. Okay. We'll let it boot for a second. All right, here's our implementation. And now for our demo. Now, sir, if you would, for me, spin the yellow knob clockwise. You know your clockwise from your counterclockwise?
I hope so.
Yeah, but no, you got to stand back and do it like this because people want to get a pretty picture. There you go. Smile. Yeah, yeah. Keep spinning it. Spin, 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 spin. Spin, spin, spin. All right. Sorry, my bad. Spin, spin, spin. Spin, spin, spin. All right. What do you see? I'll give you a hint. Look up here.
11 volts. Oh, we're pushing the pointer on the other side.
Yeah. All right. So you can stop there. Actually, yeah, it goes both directions. But I tell you what, come around this side. You can step on the thing. And push the red button. What's that? That's a reset. All right? I'm going to do it again and show people. I'll move this out of your way. So this is the way this device is designed to work. It's the way it's supposed to work. Is that we can send information about the flow from this fan or the output from our generator or the cooling rate on our coolant through this data diode in this direction, and we can read it. And out here, we can do some control things to the, yeah, you're looking at the back, aren't you? So there actually are 3 separate power supplies. We'll get into that in a second. So, and from this side, we can control stuff outside the plant, but we have no way to send data back inside this plant. Good data diodes, by the way, have separate power supplies, and I have separate battery power supplies in the back. I actually have 3. So there's no connection on that side as well. Now for some magic. Actually, all right, so I want you to flip both of those switches up. Either way, just flip them both up. You have now installed malware on both of these devices. That was easy, right? You're going to give me the grant. We'll figure out how to ship a disk for you to patch it or how to drop a USB. We'll get the malware there. But these devices are unhackable, no matter if I can get malware on both sides. So now, back around to this side for me. Get your cameras ready. And push the red button and hold it. All right. Hang on. Let's give him a round of applause here, and we'll talk about it in a second. And you can let go and or push it a few times. The fan will come back up. Like just bounce the switch a few times. Up and down. All right. So, by the way, you have now been, as far as I know, the first person ever in public to put malware on a model of a data diode and be able to jump its air gap in the wrong direction. The first ever.
That's cool.
That's cool. All right. Thank you very much for your help. You get this for participating. You knew there was some reason you were coming up. So there's your stuffed animal. Do you have a pet that likes it? Yeah, let's give him a hand. Thank you very much. All right, so I think I'll turn the fan off. It's a little noisy. So let's talk about what just happened and why. It's like, oh, he pushed the button and a thing moved. So went through the demo. That's all great. We spin it. We can turn it. Data's supposed to go this direction. Can't go back the other direction. So what actually happened? So what happened is there is additional capacity on these computers that isn't necessarily used. And so what I was able to do was to, now we've already talked about being able to transmit RF. Transmitting RF is relatively easy. Just about anywhere you can toggle a pin, you can transmit RF. Receiving RF is a little more difficult only because we usually use specialized hardware. We have an AM radio. We have a software-defined radio. We have some kind of technology that lets us decode it. But what I found here was that with a generic, these are actually Arduino-compatible little microcontrollers, there's enough excess capacity in those that without a voltage-controlled oscillator, without a mixer, without a linear amplifier, I can decode and implement a very simple software-defined radio on this other device. Just because it has lots of spare cycles, and it has an analog-to-digital converter built in it, and I can read samples off of that fast enough that over a short distance, I can receive RF through this device. So let's keep going. And kind of old, right? We've been sending RF forever. Tempest is a thing. Maybe we'll talk about that more in a minute. But people know that RF emits. But what's new, I think, if any piece of this is novel, is the ability to receive and demodulate RF without any specialized hardware. A receiver is built into the box. Sometimes these data diodes come in the same case. And they're nice and shielded to keep the noise from getting out. That also keeps noise from getting in. Are you laughing? And because it keeps noise from getting in, that makes my environment quieter, and it's easier for me to send data back and forth. I knew that's where I do. I knew. So, yeah. Well, we'll touch back on Tempest in just a second. So, here's the demo, right, the same way. We'll run the fan. This is my install malware. You give me that. It's either I emailed you an update disk, or I dropped a USB, or I found some vulnerability. That's all great. Oh, man, this is, woohoo! That was kind of fun. You push the button and it goes off. But I want you to watch something out here just for a second. What I'm going to do is I'm going to pull the wires off of this data diode. And oh, by the way, it's fairly responsive. I didn't spend a lot of time refining this, but, well, one piece at a time. So we're pulling wires off. These are the power wires. That's great. And then this is the actual receive wire. Well, I do that. There's one wire left. That's the receive wire, but there's no power going to this Optoisolator. And now I pull this final wire off. And so I've just got it laid over there, but there's no connection at all, even to the Optoisolator, and I can still send data back across this. Do what? It's pure RF. It's pure RF. I cheated just a little bit. The way I cheated here was that when I pulled this other wire off, I laid it close to the other wires to make my life easier. Again, maybe if we have the opportunity, you can come play with the distances. I get some random distance. I can change that distance depending on how robust that I want the encoding, but that probably slows my data rate. I haven't tuned it a lot. I think my data rate is probably roughly 300 baud, 300 bits a second, more or less. Now, that doesn't sound like a lot necessarily, but it's probably faster than you can type. Well, you had modems that ran at 300 baud. I did. But it's probably faster than you can type, but that's only in the wrong direction. In the right direction, this thing's sending 10 megabits, 100 megabits, a gigabit. So my inbound channel in the wrong direction is 300 baud, as fast as I can type, and my outbound channel is whatever this device was designed to run. So now we've moved from a one-time, let's drop a device, let's put some malware on, to a long-term command and control channel where we can start to explore some kind of network that's supposed to be secure enough that it needs to be protected by a data diode technology. It was too much fun not to try. Yeah. Maybe. It depends on if it's exfil. If I'm...
Repeat the question.
Oh, sorry. Well, let's get back to... Let me follow up for about what? I got... Oh, is my time up?
Yes, sir.
Okay, let me finish this one piece, and then we'll go back to that.
We got the cane.
Yeah, so... 300 baud for command and control is probably good because I can start exploring the network and get lots of pictures and data out. I could probably put some malware, but it might take overnight or a day or two or three. It's probably still a reasonable control channel. My one cheat was that I kept the wire close, but in a real environment, I'm going to be looking for LEDs, I'm going to be looking for switches, or I'm going to be looking for PC traces. I also chose the Optoisolator version because in general, you're going to be bringing PC traces close to it, so they will be close together in that scenario. So we clipped them off, and we can talk about some mitigations, or we can go to questions. I'm good for...
Perfect.
Is there any questions?
Yeah, we're going to have a lot of questions, I'm sure. Yeah.
Hang on.
Yeah, we'll do questions. That's more fun.
There you go. A couple.
My question would be, how often do we see side channel attacks on the industrial control system?
Never.
networks? Never.
Because you're not looking for them. Right?
Is it a prevalent thing?
So, why do we start to see side channel attacks? Is we start to see the side channel attacks when you guys are good. When you guys are cutting out all the easy channels, then people start moving to the harder and harder attacks. And this is a harder attack. So, you know, until you start getting your basic security right, people aren't going to be doing this. And then when you do, they're going to start moving that. Just the way we're moving attacks to devices, because we're fairly good. I'll let Rob influence me. We're good at protecting PCs. We're not quite as good as detecting other devices, so attacks move in that direction because they're not.
There's no bonus points for looking good in the conspiracy report.
Yeah. Any more questions?
Well, thank you very much, Monte. You're kind of the David Blaine of ICS, the mind freak. We'll close the summit out with that. Right. Thank you very much for.
You're welcome.
Test.
One final comment, if I would. Keep your air gaps, they're great. Keep your firewalls, they're great. Keep your data diodes, they're great. These are additional attacks. And this isn't actual hardware, this is simulation. Hopefully it spurs other people to do more research along the way. Think about air gaps, think about your security, but even if you have them, you still need to do security, right? No matter what your air gap or what your firewall, what your data diode, you need to do security. Thank you very much.
Thank you.